My name is Alfonso Berumen, and today I'll be talking about regularization techniques. Just as a review, I have up here the multiple linear regression equation. So our y is our dependent variable response, and our x's can be called independent variables, predictors, features, or inputs. So in fact, when we use linear regression, we're using the ordinary least squares method. So our prediction is generated that minimizes RSS. Well, what's RSS? In fact, stands for the residual sum of squares. So you can see here it's really based on the difference between our actual y and predicted or fitted y. So when we use OLS, we are minimizing the RSS. In fact, when we have multiple predictors or more than one independent variable, a plane is chosen to minimize the sum of the squared vertical distances between each actual value for y. So here our actual values are shown in red, these red points to the right, and the black line is just the difference between the estimated or predicted value and the actual value. Some benefits of the linear model: it's simple and easy to interpret, and we get decent accuracy. However, there are some limitations. So if the number of predictors is greater than the number of observations, ordinary least squares or linear regression cannot be used. We have some alternatives here: variable selection, dimension reduction, and regularization. So there's really a trade-off between interpretability and flexibility. So you can see here subset selection or variable selection, which we've already discussed, and Lasso, which is actually a regularization technique. They will actually give us an interpretable model, but it will lack flexibility. So in fact, least squares or linear regression gives us a little bit more flexibility, but less interpretability. So there's actually, this is related to a trade-off called the bias variance trade-off. So the basic idea here is as we get more complex, we actually may reduce the prediction error on our sample data, but that model is not going to generalize very well to any out-of-sample information or data. So we'll actually get high prediction error if we try to use that complex model on some out-of-sample data. So bias actually stands for the error introduced by approximating a real-life problem, which may be extremely complicated, using a simple model. So we got too simple. Whereas variance is actually the amount that the predicted value would change if we used new or different data. So in that scenario, we got too complex. So in terms of interpretability, it's often the case that some or many of the variables used in our model are in fact not relevant in explaining variation in y. And inclusion of these irrelevant variables leads to unnecessary complexity. So removing these variables gives us an easier to interpret model. So ordinary least squares will actually likely not produce some coefficient estimate of 0. So feature or variable selection methods actually allow us to limit our model to the best or most relevant features or variables. So just a point here on accuracy, because I am going to cover that in more detail in a bit. But if the true relationship between our y and the independent variables is approximately linear, then the ordinary least squares estimates will likely give us low bias. If the number of records is much larger than the number of independent variables, we will likely get low variance, and the model will perform well on some out-of-sample or new data. However, if n is not much larger than the number of independent variables, the likely outcome is overfitting and poor predictions on future or outside data. And again, as I mentioned, if the number of independent variables is greater than the number of records or observations, then the variance is in fact infinite, so ordinary least squares cannot be used. So what we're actually focusing on is shrinkage or regularization techniques. And so then by shrinking or constraining the estimated coefficients, we'll likely reduce the variance at a cost of a negligible increase in bias, leading to an increase in accuracy on some out-of-sample or new data. So just going through the summary of methods here, I mentioned subset selection or variable selection, dimension reduction, which would include principal components regression and partial least squares. Then finally, shrinkage or regularization, which we're covering today. So the general process there is we'll fit the model using all the independent variables. and then the coefficients are shrunken to 0 relative to the ordinary least squares estimates, thereby reducing the variance. The two methods there are ridge regression and a lasso. So some detail on shrinkage or regularization. So these methods have actually become increasingly popular with increased computational power. So for example, the first paper on Lasso was published in 1996. But the idea here is by using shrinkage techniques, we can combat overfitting and multicollinearity by reducing the overinflation of coefficients. So the general steps is we'll fit a model using all the predictors, using either ridge or lasso. And then we'll shrink or regularize the least less meaningful coefficients to 0. And the ultimate goal here is it'll reduce our out-of-sample error, particularly when we have this issue of overfitting. And just a point here, when I use beta and coefficient, those mean the same thing. So I may use those interchangeably. Okay, first with ridge. So with ridge regression, you can see there that the ordinary least squares is actually, or in part, a component of this. So you can see there in this equation to the right, RSS. So in fact, the additional component is actually what's called a tuning parameter, or alternatively lambda. And we can think of lambda as a penalty. So this penalty is going to take on a value of greater than or equal to 0, and it's going to penalize the coefficients. So in other words, there's a battle fit here, right? The RSS part of this versus the size of the coefficients, which is captured in the second term here. So, you know, we're trying to make the fit small, but then also penalize the coefficients that get too big. So in terms of the penalty, it's small, or the second term in the equation, it's small when the coefficients are close to 0. And so it has the effect of shrinking the estimates of the coefficients toward 0. So in fact, when lambda is equal to 0, the penalty term has no effect. So it's essentially equivalent to your traditional ordinary least squares linear regression results. However, the larger the value of lambda, the larger the penalty. And so then when it gets extremely large, the coefficients shrink toward 0. Yeah, the coefficients are put together in their penalty in a sum. So they're actually competing against each other. So as a result, different scales in units can actually influence the outcome, right? So predictor 1 is competing against predictor 2. And so differences in units or the scale of these two predictors may actually influence the outcome. So what we want to do is put them on a level playing field, and we do that by standardizing the predictors. So by dividing by the standard deviation, all the standardized predictors will have a standard deviation of 1. So just a hypothetical model here. This is actually pulled from a textbook. So if we were trying to explain variation in credit card balance as a function of income, credit limit, credit rating, and whether or not someone is a student, we might use ridge regression and see what the impact of lambda is, or different values for lambda is, on the coefficients. So you can think of the left side of the of this plot here as a traditional linear regression result, right? Lambda is essentially 0, right? So no effect on the coefficients. But then as lambda gets larger, the coefficients shrink towards 0. So it essentially has the effect here of biasing the coefficients, but hopefully decreasing the variance. As we talked about bias and variance. And so the larger the value for lambda, in fact, we would expect higher bias, but lower variance. So moving on here to the lasso. So the disadvantage here with the ridge regression is it includes all the variables in the model, unlike subselection. But with lasso, it's actually very similar to ridge, but uses a different penalty term. So instead of using the sum of squares of the coefficient, it uses the sum of absolute values. So it actually has the ability to shrink coefficients all the way down to 0 if lambda is sufficiently large. So then the advantage here is that it's essentially equivalent to knocking out a variable from the model if you set it to 0, right? So it's almost equivalent to subset selection when that actually happens, right? So you can see here, you can see that flat line pattern to the right here. that would actually indicate coefficient shrinking all the way down to 0. Okay, so your traditional is would be equivalent to the left here, and you can see here the differences in patterns here. So that circle should be a little bit further to the right here, but you can see here that Ridge doesn't shrink coefficients all the way down to 0, whereas Lasso actually does. So how do we select this tuning parameter? Well, typically what we'll do is choose a grid of values and select the parameter that gives us the lowest cross-validation error. So then we can refit the model using that value for lambda based on the lowest cross-validation error. So I actually used an R integration within SPSS. So SPSS is actually adapted to the open source environment. And I have some steps here and some links that will help you if you do choose to add on this extension. Can regularization be done in SPSS? It appears to be the case. So I have some visual steps here on what you would need to, the steps you would need to take to get to the regularization options. So then why did I use R integration? Well, there's actually limited documentation and examples on using SPSS and using regularization techniques within SPSS. Second, to demonstrate how one might use syntax as opposed to the dropdowns. And then also here to demonstrate how open source code such as R, Python, etc., can be used directly within SPSS. But actually, more importantly, the author of the Lasso article that I mentioned from 1996, he actually co-authored a book that relies on R. So he actually used R to demonstrate both Lasso and Ridge. Okay, so a quick case study here. So this group of authors studied TripAdvisor data, which they scraped from the internet. And what they did is actually showed that you can actually build a predictive model to explain differences in user scores, or essentially their ratings on hotels in Las Vegas. So they collected about 500 records. Just quickly here, the goals of the study. Here's the different variables or features that they were able to extract here from TripAdvisor. Just a quick table summary here. So I actually was able to analyze this data. So this data was made publicly available. So I had about 490 reviews in my data set. And so my dependent variable was score, the user score. And then I had a number of independent variables, including variables associated with the user themselves, and also the hotel as well. So here are my results here from doing just multiple linear regression. So I do have, though, some potential issues in terms of multiclinearity. So we have some rules of thumb here, but I can see here that there are some larger values for certain variables. And the numeric values I can actually test here. So this is actually a correlation matrix. So I can see here, though, that the number of reviews and number of hotel reviews, and also number of helpful votes, these are all correlated or highly positively correlated variables. Okay, so then I used a grid of values for lambda, and you can see here how it impacts the coefficients and how they shrink towards 0 for both Ridge and Lasso, and you see that flat line at a certain point for the Lasso, where coefficients are being set all the way down to 0. So I used, as I mentioned, cross-validation to select the best value for lambda, then fit the models and was able to generate these coefficients. So you can see here the difference between the Ridge result, the Lasso result, and how that impacted the coefficients. And then when compared to the OLS, you can see the difference there as well. And one thing to point out, though, is that Lasso actually set some of the coefficients all the way down to 0, which is indicated by those missing points to the right here. Okay, so just a review of error. Again, the difference between the predicted and actual. So in fact, there's all these other all these resulting error metrics that we can generate, including the root mean squared error, mean absolute error, mean absolute percentage error, and mean squared error. So here's the detail and equations to generate these summaries, or these basically average summaries of our difference between our actual and predicted value. So when I compare the accuracy here, I mentioned that I was going to discuss prediction accuracy in a little bit more detail. So when I compared the accuracy here, in fact, the results from regression versus ridge versus Lasso for this particular data set didn't vary a ton. So in fact, what was published, so here's an example here of the actual versus predicted. But in summary, what was published here was a mean absolute error of 0.745. So on average, in absolute value, the author was off by 0.745. And in terms of mean absolute percentage error, on average, the prediction was off by 27.32%. And if you look at my results here, they're in fact pretty similar. So regularization didn't give me a huge bump in terms of accuracy, but it was still an interesting exercise to compare the regression results to the regularization result. Okay, so I just wanted to show you real quickly here in SPSS how you can use open source code. So I'm going to go to File, Open, and then syntax here. I actually have some syntax file prepared here, so I'm going to hit Open. And so you can see here it actually pulled up a a screen here, so I can actually code interactively. And to use R, in fact, you have to start by saying begin program R, and then to close it, you'll have end program at the end here. So I'm actually going to open up here my R program. So I'm going to copy this this code here. Go back here. So all I have to do there is then paste that in. And then I'm going to go ahead and select here and then press this play button to run. So then you can see here all the graphics and all the results that I showed you in the presentation were produced directly in SPSS. And that's it.